Hello, my dear children. Welcome to the mathematics class. Today we are going to discuss application of integrals. In this chapter, we are going to discuss the concepts of exercise 8.1. In the previous class, we have discussed finding the or evaluating the definite integral of a given function by using properties of definite integrals. I hope you have learnt. I hope you have learnt well. I hope you have understood well the concepts of evaluating definite integral of a given function by using properties of definite integrals. Haven't you, my dear children? Right. Now come to this exercise. Are you ready to listen the class? Right. In geometry, we have learnt formulae to calculate areas of various geometrical figures, including triangles, rectangle, trapezium, and circles. In earlier classes, we have studied the formulae for finding areas of these simple geometrical figures. Such formulae are fundamental in the application of mathematics to many real life problems. Okay, my dear children. The formula of elementary geometry allow us to calculate areas of many simple figures that are used only for simple figures. That formula are used for finding areas of simple figures. Okay, my dear children. However, they are inadequate for calculating the areas enclosed by the curves. For that, we shall need some concepts of integral calculus. So, we are using integral calculus for the remaining cases. Okay, my dear children. Right. Now, come to this first point. Area under simple curves. How to find area of a region under the simple curve. Let f of x be a continuous function defined on closed interval AB. See this figure. This is a geometrical representation of y is equal to f of x. This is a curve. Okay, my children. Curve of y is equal to f of x in this closed figure A to B. Then the area bounded by the curve y is equal to f of x, the x-axis, and the ordinates x is equal to a and x is equal to b is given by capital letter A. Capital letter A denotes area of the region bounded by the curve y is equal to f of x, x-axis, and the ordinates x is equal to a and x is equal to b. Okay, my children. How to find integral a to b? Integral a to b f of x dx, or simply we can write integral a to b y dx, because y means f of x only. Understood this point, my dear children? So here if you observe, this is a graph of y is equal to f of x. Here this is the interval x is equal to a and x is equal to b. This is the region bounded by this curve y is equal to f of x, the x-axis, and the ordinates x is equal to a and x is equal to b. This entire region denotes the area bounded by the curve, the x-axis, and the ordinates x is equal to a and x is equal to b. To find this region, we have no particular formula. In this case, we use the concepts of definite integral like this. Okay, my student. We can think of area under the curve as composed of large number of very thin vertical strips. See here, a thin vertical strip is considered. Like this, a large number of vertical strips are there. Here we can draw a large number of many vertical strips are there. Consider an arbitrary strip of height y. This is a height of this vertical strip, thin strip, and width is dx. The width of this vertical strip is dx. Then dA denotes area of the elementary strip. This strip is called elementary strip. Okay, my children, what is this thin vertical strip is called elementary strip, is equal to y into dx. Length into breadth. Yes or no, Marichalan? This is in the shape of a rectangle. So length into breadth. Length is y and breadth is dx. Okay, Marichalan. Where y is equal to f of x. This area is called the elementary area, which is located at an arbitrary position within the region which is specified by some value of x between a and b. Okay, my children? Understood? We can think of the total area of the region between x-axis, ordinates x is equal to a, x is equal to b, and the curve y is equal to f of x as the result of adding up the elementary areas of thin strips across the region P, Q, or SP. Let us consider these are points P, Q, or SP. This entire region, the area of this entire region can be found by adding up these areas of vertical strips, elementary strips. Symbolically, we express capital letter A is equal to integral A to B dA. That is equal to integral A to B y dx. Previously, we have defined dA means y into dx. Yes or no, my children? Length into breadth. So, sum of all these areas of these vertical strips, then we get the area of this entire region bounded by the curve y is equal to f of x and the x-axis and the ordinates x is equal to a and x is equal to b. That is equal to integral a to b f of x dx. Understood this point, my children? In this case, we use integral calculus. We use the definite integral to find the area of the curve. Okay, my children? Understood? Right. Now come to the second point. The area of the region bounded by the curve x is equal to g of y, y-axis, and the lines y is equal to c, y is equal to d is given by area a is equal to integral c to d x dy. That is equal to integral c to d g of y dy. Okay, my children. The previous point we have discussed the area of the region bounded by the curve y is equal to f of x. But sometimes the equation of the curve will be given in terms of like this: x is equal to g of y. In that case, we have to find sometimes by taking y-axis as base. In the previous in the previous point, we have taken x-axis as base. On that base, the required region is standing on that x-axis. But here on y-axis, that required region, okay, mentioned on y-axis, and the lines y is equal to c and y is equal to d. Between these two lines, we have to find the area of the region bounded by this curve x is equal to g of y and y-axis. Understood this point, my children? Understood the difference between the previous point and this point? Yes. Here we consider the horizontal strips as shown in the figure given below. Here, see there we have taken horizontal strips, very thin horizontal strips. There are large number of horizontal strips are there. We consider like this elementary horizontal strips. By adding the areas of all these all elementary strips, we get the area of this entire region. Here the length of this horizontal strip is x and width of this horizontal strip is dy. So integral x dy, length into breadth. Integral means it is nothing but summation. Okay, my children, remember this point. Integration means summation. So sum of these all elementary areas, we get the entire area, the area of the region bounded by the curves and the given lines. Understood this point, my children? Right. Now come to remark. We have to notice these points also, my dear children, when you are finding area of the region bounded by the curves. See here, see this point. If the position of the curve under the consideration is below the x-axis, then since f of x is less than 0, from x is equal to a and x is equal to b as shown in the figure given below. Observe this figure, my children. This is a graph of y is equal to f of x. If you observe this curve, this is under the x-axis, below the x-axis. As it yes or no, my children? This is a region bounded by the curve. This region is below the x-axis. In this case, we get a negative value. Okay, my children, given below. The area bounded by the curve, x-axis, and the ordinates x is equal to a, x is equal to b comes out to be negative. In this case, if the curve is below the x-axis, then if you are finding the area of the region bounded by the curve x-axis and between x is equal to a and x is equal to b, we get negative value. But can you get area of a region a negative value? Not at all. It never be a negative. Area of any region should be positive. No negative. It should not be a negative value. But it is only the numerical value of the area which is taken into consideration. So we have to consider only numerical value. We should not take its magnitude. Thus, if the area of its negative, if it is a negative value, we take its absolute value. That is, area is equal to modulus of integral a to b f of x dx. In this case, if we get this integral a to b f of x dx a negative value, in that case we have to take its absolute value, because we are finding here area of the region bounded by the curve on the x-axis and between the lines x is equal to a and x is equal to b. So since this numerical value represent area of region, it should be a positive value. Sometimes we get a negative value. In that case, we have to take its magnitude, modulus. Understood, my dear children? Understood this point? Notice this point, my dear children. Sometimes we come across these kind of cases also. Okay, my dear children? Right. Now come to the second remark. You have to notice this second point also, my dear children. Generally, it may happen that some portion of the curve is above the axis and some is below the x-axis, as shown in the given figure. See this figure. This is a graph of y is equal to f of x. This is a graph of y is equal to f of x. Here the interval x is equal to a, this is x is equal to b. In this interval, if you want to find the area of the region bounded by this curve y is equal to f of x, in this interval a to b. So here this region is below the x-axis and this region is above the x-axis. Okay, my children. Here a1 is less than 0. The area is below the x-axis. Therefore, you get here area of this region is negative. Yes or no, my children? Here area of the region is positive because this region is above the x-axis. And a2 is greater than 0. This region is greater than 0. Therefore, the area A bounded by the curve y is equal to f of x, x-axis and the ordinates x is equal to a and x is equal to b is given by a is equal to capital letter A is equal to modulus of a1 plus a2, because here we get a negative value. In the previous point we had discussed, if the curve is below the x-axis, in such case, if you find the area of the region bounded by the curve, we get a negative value. In that case, we have to take its absolute value. We should not consider negative sign. Okay, my teacher, understood this point? Right. Now come to the third point. In order to find the area of the bounded regions, we may use the following algorithm. We use these following steps. Okay, my children, to find the area of the bounded region, we follow these steps. Remember these steps, my dear children. These are very important. See the algorithm. Step 1. First step, make a rough sketch showing the area to be found. We have to draw a rough sketch showing the area to be found. Rough diagram. We have to draw a rough diagram. Okay, my dear children. Step 2. Slice the area. We have to cut that area into horizontal or vertical strips as the case may be. According to the question, according to the graph of the function, we have to slice, we have to make into small pieces into horizontal strips or vertical strips according to the condition. Okay, my children. Now come to the third step. Consider a representative strip and the corresponding approximating rectangle. We have to draw a approximating rectangle. Okay, my children. Now step 4. Find the area of the approximating rectangle. If the representative strip is parallel to y-axis, then its width is taken as delta x. And if it is parallel to x-axis, then its width is taken as delta y. Okay, my children. The vertical strip length is and width is taken as delta x. And here in this case we take width of the rectangle is delta y. Okay, my children, understood this point? Right. Now observe these two figures, my children. Figure 1, this is a figure 2. In this figure, the approximating rectangle is RQLM. RQML. Here RQML. This is approximating rectangle. Very thin slice, thin vertical strip. It is in the shape of a rectangle. In figure 1, RLMQ is the approximating rectangle of area y into delta x with length of this vertical rectangle is y and width is delta x or sometimes dx. We can take it as dx or delta x. So length into breadth. And in the figure 2, in this figure, the area of the approximating rectangle, the area of this very thin rectangle, RLMQ is x into delta y. Here length of this rectangle is x and width of the rectangle, thin horizontal strip, that is delta y. Width of this rectangle, delta y or dy. Sometimes we can take it as dy also. Both represent the same, delta y or dy. Delta x and dx denote the same. Okay, my children, understood this point. Now come to the step 5. Find the limits within which the approximating rectangle can move. In the figure 1 above, see this figure, in the figure 1 above, the approximating rectangle area y into delta x can move between the lines x is equal to a and x is equal to b. See, this rectangle is moving this along this line x is equal to a and x is equal to b between these two lines. Yes or no, my children? Therefore, the area bounded by y is equal to f of x, y is equal to 0, nothing but x-axis. Y is equal to 0 means x-axis. X is equal to a and x is equal to b is given by capital letter A is equal to integral a to b y dx. Understood this point, my children? Right. In figure 2, observe this figure, my children. In figure 2, the approximating rectangle of area x into delta y. The area of the rectangle, length into breadth, that is x into delta y. It can move between the lines y is equal to c and y is equal to d. This rectangle, there is a horizontal rectangle is moving between the lines y is equal to c and y is equal to d. Understood this point, my children? Therefore, area bounded by x is equal to g of y, x is equal to 0, it is nothing but y-axis. X is equal to 0 means y-axis, y is equal to c and y is equal to d is given by capital letter A is equal to integral c to d x dx. Understood this point, my dear children? Here integration means the sum of all the areas of the thin strips, horizontal strips, whereas here we are adding up the areas of all these vertical strips. Understood this point, my children? Integration means addition. Okay, my children, understood this point? Keep this point in your mind. Right. The concepts of exercise 8.1 were finished. Okay, my children, they were completed. Now come to the sums in the exercise 8.1, page number 365 in the textbook. Okay, my dear children, by using the concepts, by using the previous knowledge, we find the area of the region bounded. Okay, my dear children, see the question number 1. Find the area of the region bounded by the curve y square is equal to x and the lines x is equal to 1, comma x is equal to 4 and the x-axis in the first quadrant. Okay, my dear children, to find the area of the regions bounded by the curves, you should have some idea about graphs of the curves for the given equations. Okay, my children, right? What is the equation here given? What is the equation of the curve? Y square is equal to x. Given equation, is y square is equal to x. This is the equation of the curve given to us. Previously I told you you should have some idea about the graphs of the given equations. So y square is equal to x. What is the graph of this equation? Yes, it is a parabola. It is a parabola and it is a symmetrical about x-axis. Yes or no, my children? So let us draw a rough diagram. Let us draw a rough diagram. Let us follow the steps. We have discussed the algorithm. What are the steps? First we have to draw the rough diagram. We have to draw the rough diagram. The graph of this equation is a parabola symmetrical about x-axis. This is a parabola and symmetrical it is a symmetrical about x-axis. Okay, my children, understood this point? So this is a graph of the given curve. After drawing that rough diagram, let us take the limits. Here like x is equal to 1 and here x is equal to 4. So in the first quadrant, the graph of the curve is in the first quadrant as well as in the fourth quadrant. But they asked as the area of the region bounded in the first quadrant. So we should consider this part of this region only. Okay, my children. So this part of the region is standing on x-axis. So let us consider vertical strips. Okay, my children. Dx. That is y. Okay, my children. So y into dx. Yes or no, my children? So let us find the value of y from this equation. So y square is equal to x. This implies y is equal to plus or minus root x actually. But it is in the first quadrant. We consider here root x only. Okay, my children. Now this implies y is equal to root x. We consider positive sign because it is above the x-axis. This region is above the x-axis. If it is below the x-axis, we take minus root x. Y is equal to minus root x. Understood this point, my children? Right. So we found y. So length of this vertical strip is root x. Okay, my children, this is dx. Understood this point, my children? Y dx. Okay, my children, y means root x into dx. Now what are the limits from which number to which number? What is the interval? 1 to 4. As for the my children. So this is, let us consider this is A, B, C, D. This is the region bounded by the curve and the x-axis, and between the lines x is equal to 1 and x is equal to 4. Let the region bounded by the curve y is equal to y is equal to root x, x-axis, lines, ordinates x is equal to 1 and x is equal to 4 is ABCD. This is the name of this region, ABCD. Okay, my children. Therefore, area of this region ABCD, area of the region ABCD is equal to integral 1 to 4, limits from 1 to 4. Understood this point, my children? Integral 1 to 4. What is the area of this thin vertical strip? We considered here vertical strips. So y dx by taking by considering here vertical strip. Okay, my children. So y into dx. Y is the length of this thin vertical strip and dx is the width of this thin vertical strip. Understood this point, my children? That is equal to integral 1 to 4. What is value of y? We have found y is equal to root x dx. Hereafter we use the previous knowledge. We integrate this function. Okay, my children. After that we apply the limits. Okay, my children. Right. That is equal to integral 1 to 4. This can be written as 1 by x power 1 by 2. Yes or no, my children? Root x can be written as x power 1 by 2. Understood this step, my children? Root x is written as x power 1 by 2 dx. Okay, my children? Understood? Right. That is equal to x to the power of 1 plus 2 by 1 by 2 plus 1. Okay, my children? Limits 1 to 4. Because integral x to the power of n dx is equal to x to the power of n plus 1 by n plus 1. X to the power of n plus 1 by n plus 1. By using this integral formula, we got this step x to the power of 1 by 2 plus 1 by 1 by 2 plus 1, where n is equal to 1 by 2. Understood this step, my children? Right. This is equal to x to the power of 3 by 2 by 3 by 2. Limits 1 to 4. Okay, my children, by simplifying these two numbers, we get x power 3 by 2. We get the same number in the denominator. Okay, my children. Here 3 by 2 is a numerical coefficient. We can write it outside. So it becomes 2 by 3 because it is in the denominator. We are bringing this new denominator into the numerator, then it becomes 2 by 3 into x power 3 by 2 limits limits 1 to 4. Okay, my children. So in this function, we apply the upper limit minus lower limit. Do you remember that steps, my children? Right. 2 by 3 into 2 by 3 into what is upper limit? 4. 4 power 3 by 2. We substituted upper limit in this function minus in the same function we substitute lower limit 1 power 3 by 2. Okay, my children, understood this step? Right. That is equal to 2 by 3 into this can be written as 2 square whole power 3 by 2 minus 1. 1 power 3 by 2 is the value is 1 only. Understood this step, my children? Right. Here 2 gets cancelled. Okay, my children. 2 power 2 cube minus 1. We get 2 cube minus 1 only. Understood this step, my children? Right. 2 by 3 into what will get? 2 cube value is 8 minus 1. 2 cube is 8 minus 1. Understood this step, my children? Right. That is equal to 2 by 3 into 8 minus 1. What is the value of 8 minus 1? 7. Understood this point, my children? Right. That is equal to 2 sevens are 14 by 3. Understood this step, my children? This is the square units. Square units. Because this is area of the region bounded by the curve. Okay, my children? And the x-axis, and between the lines x is equal to 1 and x is equal to 4. Understood this point, my children? Right. Here I am not explaining question number 2. Please try the question number 2 yourself, my dear children, because question number 2 is the same as that of question number 1. Just equation of the curves and the limits were changed. The procedure is same as that of question number 1. Will you try the question number 2 yourself, my dear children? Please try it. If you have any doubts, ask your doubts and get your doubts clarified. Okay, my dear children? Right. Come to the question number 3. Find the area of the region bounded by x square is equal to 4y, y is equal to 2, y is equal to 4 and the y-axis in the first quadrant. Understood this point, my dear children? Right. Now, what is the given curve? X square is equal to 4y. Previously, I told you, you should have idea about curves, graphs of the equations, or graphs of the given equations. Here, x square is equal to 4y. It represents a parabola. It is symmetrical. It is symmetrical about positive x-axis, positive y-axis. Okay, my dear children, like this. X square is equal to 4y. This is a rough diagram. This is graph of this equation x square is equal to 4y. You should get some idea. You should have some idea about the graph of this given equation of the curve. Okay, my dear children. So this graph of this equation is a parabola and which is symmetrical about positive y-axis. Okay, my dear children. This is a parabola and symmetrical positive y-axis. It is symmetrical about positive y-axis. Okay, my children. Now the limits. What are the limits? Y is equal to 2. Here 0, 1. Here 2, 3, 4, 5. So y is equal to 2. See here, this is y is equal to 2. This is the graph of y is equal to 2. and y is equal to 4. This is graph of y is equal to 4. This is the line parallel to x-axis. Y is equal to 2 is parallel to x-axis. Okay, my children. So this is the region. You have to find the area of this region. Let us consider this is the region. A, B, C, D is the required region. Area of this required region. So if you observe this region, this is standing on the y-axis. It is also asked here about y-axis. So we take here horizontal strips. Horizontal strips. Okay, my children. Here x dy. The length of this vertical horizontal strip is x, and width of this vertical horizontal strip is dy. Okay, my children. X dy. X dy is the area of this thin horizontal strip. Okay, my children. Therefore, area of the region. Otherwise, let's write the region. So from this equation, let us find x value. Let us find x value. So we have to find x value into dy. Okay, my children. From this equation, let us find x square is equal to 4y. This implies x is equal to plus or minus 2 root y. Okay, my children. But x is equal to, we take root 2 root y only. 2 root y. Because this region is in the first quadrant, it is positive. So we take plus 2 root y. Okay, my children. Since region is in first quadrant, the required region is in the first quadrant. So we are taking here positive value. Understood this step, my children? Right. Now let us consider that the region bounded by the curve x is equal to 2 root y. X is equal to 2 root y. Okay, my children. X is equal to 2 root y. Y axis and y is equal to 2 and y is equal to 4 is ABCD. Let us consider this region is ABCD. Therefore, area of ABCD integral 2 to 4, limits you know here 2 to 4. This horizontal strip is moving between y is equal to 2 and y is equal to 4. Yes or no, my children? So integral 2 to 4 x dy. Okay, my children. That is equal to integral 2 to 4 by taking horizontal strips. By taking horizontal strip, this is x dy is the area of the rectangle, area of this horizontal strip. So integral means the sum of, we are adding up all the areas. Understood, my children? Right. What is the value of x here? 2 root y. Okay, my children? 2 root y. 2 root y dy. Because x is equal to 2 root y. Understood this step, my children? Now we use the concept of definite integral. Finding the definite integral of a given function. Hereafter we use concept of definite integral of a given function. Okay, my children, 2 into integral 2 to 4. Here 2 is a numerical coefficient. So I wrote it before the integral sign. Understood the point, my children? Into integral 2 root y dy. Understood this step, my children? Right. That is equal to 2 into integral 2 to 4 y to the power of 1 by 2 dy, because root y can be written as y power 1 by 2. Yes or no, my children? Right. Now it is in the form of integral x to the power of n dx. Yes or no, my children? So 2 into y power 1 by 2 plus 1 by 2 plus 1, and limits are 2 to 4. Integration part is over. We are writing here limits of this integral. Okay, my children? Right. 2 into y power, what you get here, 3 by 2, by the denominator also 3 by 2, limits 2 to 4. Understood this step, my children? Right. That is equal to 2 into 2 by 3, and taking this fraction to the numerator, then it becomes 2 by 3. Understood this point, my children? Into y power 3 by 2, limits 2 to 4. So in this function, understood this step, my children? In this function, we substitute upper limit minus lower limit. Okay, my children? 2 2s are 4 by 3 into 4 to the power of 2 by 3, 4 to the power of 3 by 2 minus 2 power 3 by 2. Okay, my children, understood this step? I substituted upper limit in this function minus lower limit 2 power 3 by 2. Okay, my children? Right. That is equal to 4 by 3. This can be written as 2 square whole power 3 by 2 minus, this can be written as root 8. 2 cube is 8. So square root of 8. Understood this root 8, my children? Right. Here 2 gets cancelled. 4 by 3. Here 8 minus 8. 2 cube minus 8 minus root 8. Okay, my children? Square units. This is the area of the region bounded by the curve x square. X is equal to x square is equal to 4y. Y is equal to on the y axis, and y is equal to the between the lines y is equal to 2 and y is equal to 4 in the first quadrant. Understood, my dear children? Right.